this computer. Wonderful. Okay. Thank you so much for suggesting B courses. Hopefully that means that some people will see this, or some more people might see this. Great. Let me now figure out my screen share again. Share my screen, share. Awesome. I'm assuming everyone can see this. Yes? Okay, thank you. Okay, wonderful. Well, thank you everyone for logging in on Zoom. I am really sorry that I'm not there in person, but given the times, it seems prudent to stay at home. So today's lecture is going to continue where we left off last time, and we're going to talk about the separating hyperplane theorem and convex functions. If we have some time, we might start talking about gradient descent. If we don't have time, then we might move that to the next class, depends on how things go. But we're going to talk about the separating hyperplane theorem, which we started with last time. And so here, I just wrote out the statement in advance since we already talked about it last time. So let C and D be two convex sets and let them be disjoint sets. So let's say that their intersection is empty. Then we know that there exists a hyperplane. We know that the equation of a hyperplane can be represented by A transpose X equal to B, such that for every X in C, you have that A transpose X is greater than B, and for every X in D, you have that A transpose X is less than or equal to B. And remember that we can also write hyperplanes in another way. We can write them as A transpose times X minus X naught equal to 0. And so here we might want to write as A transpose X minus X naught greater than or equal to 0 for one side, and A transpose X minus X naught less than or equal to 0 for the other side. Okay? So last time we didn't talk about some tricky cases that can arise in this situation. In particular, we did not talk about the case where some of the sets might be open, or you might have unbounded sets. And it might not be obvious that actually you can find separating hyperplanes in some tricky cases. Even though the sets are clearly convex, separating hyperplanes can be tricky, but it turns out that they absolutely exist. So for example, let's consider the following two sets. The first set is this set C, which is the set of all pairs X and Y. So let's say this is the X-axis and this is the Y-axis. And it's all points where the X value is less than 0, right? So it's everything to the left of the axis. And what if I considered my second set D to be given by this expression here? So I'm looking at all of those points such that X times Y is greater than 1. So that means that basically Y is greater than or equal to 1 over X, right? And if I draw this now, this is my, Y equal to 1 over X curve. And so Y greater than or equal to 1 over X is basically everything that's here, right? Now, both of these are unbounded sets. Is in the largest value in these sets is, has no upper bound. Are both of these sets convex? The answer is yes, right? So for example, if I was to take any 2 points here and draw them, the line segment is contained inside. Any 2 points here, the line segment is contained inside. You could formally prove this. Here we'll just do a proof by picture. What is the separating hyperplane for these two sets? Anyone? Please do interact in the chat, because otherwise I will have no way of knowing if you're with me or not. It's the X equal to 0 line, right? So basically, this line here is what would be this hyperplane here would be our separating hyperplane. But as you can see, it's basically the boundary of one of the sets. It's basically right there. And so we have this, tricky situation. And so this is a particular situation where we can see how the separating hyperplane exists, but it's not a case that we're going to be able to deal with in the proof that we're going to talk about. The second case of slightly challenging situation was brought up by some of your colleagues in class last time, which is the case in general of open sets, and especially open sets that might be touching. So for example, if you have this convex open set here and this convex open set here, so what this means is that the set C and like the D set is everything inside the pink dotted line but not the boundary, and here the set C is everything inside the blue dotted line but not the boundary. Let's say these boundaries intersect at this one point, then again you can see that a separating hyperplane will exist here. But again, a separating hyperplane will exist here, but again, it's going to be difficult to deal with this particular situation in the proof that we're talking about. So we're going to talk about a limited proof for the case of closed and bounded sets, basically where you can actually show that the minimum distance between the two sets actually exists, and those 2 points C and D that we talked about last time actually exist. I was hoping that I could give like a short sketch of the general proof, but you need quite a lot of advanced techniques from topology, and I didn't think it would be worth it to spend the time in the classroom going over this, so I'm not going to. But the spirit of the idea will be conveyed in the second proof. But you have to, for the general case, when you want to be able to, for example, consider open or unbounded sets, you have to consider many kind of limiting cases, nesting of different sets, more complex constructions for these separating hyperplanes. So we're not going to talk about that in the context of the class right now. I see there's a question in the chat. For set D, are we assuming that X is always positive, right? Otherwise, we couldn't have divided by it to get a bound for Y. Yes, so here we're ignoring the case of X equal to 0. That's correct. Basically, you want to think about that as the limit of X goes to 0. Okay, good. Everyone with me here? Everyone clear on what we're going to try to do? Yes? No? Okay, thanks. Okay, so now we have some setup, which we talked about last time, so I'm going to go through it kind of fast. So here I want to consider basically some set C and some set D. I'm drawing these as very far apart so that there's plenty of distance between these two sets, just because I want to be able to draw a picture. And now I'm going to consider basically the vector that joins these 2 points. So this is my C and D. And I'm going to define the distance between the set C and the set D as this infimum. You can just think of it as a minimum for most purposes of the Euclidean distance. So in particular, I want to think about the 2 norm, the infimum between all points X, where X belongs to C and Y belongs to D. So basically, I'm going to consider all different points here. So there's some point X here, and some point Y here, and maybe some other point X, and some other point Y. And I'm going to look at the pairwise distances here, here, so on and so forth. And I'm going to identify what is the minimum distance, okay? And once I identify that minimum distance, I'm going to let C be the point in set C that attains that minimum distance, and D be the point in set D that attains that distance, right? So let C belonging to C and D belonging to D be the 2 points that are closest to each other from these 2 sets, okay? And basically, because we're going to assume that these are closed and bounded sets, we can infer that C and D exist and are distinct. So in particular, we're not going to deal with the case that C minus D is exactly equal to 0. Okay, so that is a trickier case, and we're basically simply not going to handle it in the class. It's just out of scope. Okay. So now what did we do? We said that, well, if I have these 2 points that are, one is in C, one is in D, and I want to separate them with a hyperplane, what's a good candidate hyperplane? Well, just looking at this picture, I'm saying, why don't I take the hyperplane that kind of divides this line segment into 2? So I find the midpoint of this line segment, which is C plus D divided by 2. And then what I do is I say, let me consider the hyperplane that is normal to this line segment at this particular point. So in particular, let me consider the hyperplane such that the normal vector for the hyperplane is given by this quantity, which is D minus C transpose, or this vector D minus C. And I want to also have the hyperplane pass through this particular point, which is the midpoint of the line segment. And that midpoint of the line segment is this quantity here, half D plus C vector, okay? So is everyone clear how this red line is the hyperplane that we want to consider? Any questions around this? Good. So this is the hyperplane perpendicular to D minus C, and it's passing through this midpoint, D plus C by 2. Okay, so last time in lecture, you all computed basically that f of D is 1/2 D minus C squared, and so it's always greater than or equal to 0, and f of C is always less than or equal to 0. Okay, so that's kind of where we left off, and we'll pick up the proof from there on up, okay? So we clearly see that C and D are on 2 separate sides of this particular boundary. And now what we want to do, why is my hand raised? Weird. I don't know how to deal with that, but okay. How do I unraise my hand? Reactions, lower hand. Okay. Sorry about that. Okay, so now we have these 2 things. We want to show, right, that in fact, for every x, let's say, belonging to the set D, that f of x is greater than or equal to 0. And for every x belonging to the set C, that f of x is less than or equal to 0. And we're going to show this proof by contradiction. So, okay, we're going to try a proof by contradiction. And in particular, we're going to assume there exists some vector u that belongs to D such that f of u is strictly less than 0. Okay? So we want to prove that it's greater than or equal to 0 for all vectors in D. So let's let's say there exists some vector in D such that it's less than 0. Now note that we also want to show that for every vector in C, f of x is less than or equal to 0. What we're going to do is we're going to show this case for u belonging to D, and then the proof for the vectors that would belong to C would follow analogously. And so we don't have to do that secondarily explicitly. So we're just going to focus on this one case, okay? So let's now evaluate f of u. Okay, what is f of u? Well, just plugging in, we have this equation here, right? For f of x, or f of u. So we have D minus C transpose, and then u minus D plus C divided by 2. Okay? And then we're just going to do some algebraic massaging to get this into a form that is convenient for us. So here, what I'm going to say is that in this expression, I'm going to say consider u minus d plus d minus d plus c over 2. I just added and subtracted the same term. Clearly, I haven't changed the value of f of u, right? This is obviously equal to each other. But it allows me to pull this out and write this expression as d minus c transpose u minus d. And then just simplifying the term here, so pulling that d in, what I can write this as is plus 1/2 d minus c. Okay? And this further, I can now write as the inner product between d minus c and u minus d plus 1/2 of norm squared d minus c. Right? So I'm trying to basically figure out whether f of u is positive or negative, right? And I'm assuming that it's negative. And so what I've done by doing this kind of reformulation is I've pulled out a part of this that is always strictly non-negative, right? We know that this term is always going to be greater than or equal to 0, right? And so given that this term is always going to be greater than or equal to 0, what that means is that if I want to have f of u be strictly less than 0, and I have f of u is some term plus something that's greater than or equal to 0, this first term has to do the job of pulling that quantity below 0, right? So this implies that this inner product, d minus c, u minus d, had better be strictly less than 0. Does everyone see that? Yes? No? Okay. Type questions into the chat. I see 3 people with questions. Okay, someone doesn't quite see this. Okay, so basically I have this quantity. So I have f of u. So I have some I don't know, let's call this some p is equal to q plus r. Okay? P is negative. And so if it's equal to q plus r, then q plus r had better be negative, right? P is negative implies q plus r is negative. And if r is now strictly greater than or equal to 0, then the only way that q plus r can be negative, if q was positive and not or also non-negative, then q plus r would always also be greater than or equal to 0, right? So for q plus r to be less than 0, it has to be less than q has to be less than 0 as well. And in this case, q is this inner product. Okay, so I hope that helps. Okay, great. Good. So now we have this, and we want to now use this to kind of arrive at a contradiction. Okay? So how are we going to think about this? So let's think about this, geometric interpretation. So I see that there's some other like alternative interpretations in the chat. That's great. Feel free to talk to each other and figure it out. I don't know that I'll be able to get to every single conversation, but please go ahead and discuss in the chat. Okay, so when I'm thinking about this, I want to think about, let me draw this vector d minus c. So this is my d, and this is my c, okay? And I have my vector u minus d. And u minus d, I know, forms an obtuse angle with the vector d minus c. So if I arrange the heads of the two vectors together, then I know that they must have this obtuse angle, okay? Does everyone see this? Okay, this is because their inner product is negative. We talked about this a little bit in the last class. So now u minus d is a direction, and I can use it to move from any starting point. In particular, remember, I want to try and get a contradiction to, to something, given that I have now assumed that there is this u that belongs to d and f of u is less than 0. One thing that I could get a contradiction to is the minimality is the minimality of the distance between the points D and C. So I've said that D and C are the closest points to each other, but if I could somehow find some other point that also belongs to the set D, but is closer to C, then I could get at the contradiction that I wanted. And this geometric picture helps me see how I might arrive at that contradiction. In particular, if I consider this u minus d, but I put the head of the vector at the point D. So I'm walking along, let's say I'm walking along this vector u minus d, but I'm starting from point D, okay? So then, because of the fact that this inner product is negative, what I can say is that if I move along the vector u minus d for some distance, let's call it t, then I may get closer to the vector c. Okay, so clearly I'm basically trying to think of what multiple of u minus d can I move along. If I took a very large multiple of u minus d, clearly I'm not going to get closer to c than d is. I might get very, very far away, right? So this is not true for every t, but can we maybe show that there exists some t that this is true, right? If you look at this picture, for example, moving along this vector, there might be a point somewhere here that is actually closer to C than D is. Does everyone see that? Okay, good. So let me consider this point. So consider the point that you start at D and then you move for t units along the vector u minus d. And let's call this point P. Okay? So this point P I can further write as t times u plus 1 minus t times d, right? Does everyone see this? This is just a rearrangement. So now we know that D is a convex set. And U belongs to D, and D belongs to D. So if T belongs to 0, 1, this means, what can we say about P? P is now a convex combination of two vectors that are both in D, right? Therefore, this point P must also belong to D. Does everyone see that? But this is not true for all T. This is only true for these T's that are between 0 and 1. Okay? So we have some restrictions on T, but let's keep them. Okay. So now we want to consider what is the distance between this new point P, this new vector P that we found, and our original C. So consider now the distance between C and P. Okay? Well, let's just fill in the I'm sorry, excuse me. So let's fill in what we have. So we have C minus D minus T times U minus D. Right, I'm just filling in the definition of P here. Okay, so this norm squared, I can compute just like I would any other norm squared. So I'm going to write it as C minus D minus T times U minus D transpose times C minus D minus T times U minus D. Okay? And this now further I can write as the norm squared of C minus D. And then I have plus T squared times U minus D norm squared minus 2 times the inner product of C minus D and U minus D. Okay, does everyone see this? What we've done? So I just did a little bit of massaging. What do we want to show? We want to say, we want to consider this distance, and we want to be able to basically say that that P is closer to C than D is, right? So I want to have that this distance is smaller than this distance, right? Does everyone see that? Yeah, I missed this is a T here. I want to show that this is less than this. So for this to be less than this, what do I need to show for this quantity here? I want to show that this is negative. Right? Yes, no, maybe. If I can show that this is negative, then I will be able to show that basically P is closer to C than D is, right? So let me try to investigate this term. Okay, good. So let me consider this. T squared U minus D squared minus 2T C minus D u minus d. Okay. Oh, thank you for the virtual nods. That's sweet. So I can rewrite this u minus d squared. Instead of having this minus, I'm going to rewrite this in a way that makes it slightly more obvious what I'm going to do next. D minus c times u minus d. Okay? So what's the advantage of writing this in this way? What do we know about the inner product between d minus c and u minus d? We know that this is negative, right? So I want this whole thing to be negative. I want, let me use a different color. I want this whole thing to be negative, okay? I've already restricted my t to be greater than 0, so I can just cancel a t and rewrite this as t times u minus d whole squared plus 2 inner product d minus c u minus d. And I want this to be less than 0. So now this quantity here, this quantity here is strictly less than 0. Okay, so that means there's a little gap between this and 0. So now, if I could make this small enough so that it would fit into that gap, would I be done? Basically, because of the fact that this is strictly less than 0, which means that, 0 is somewhere here and this quantity is somewhere here. There's always a gap. And if I could make t times u minus d fit exactly into this gap somewhere, then what is this sum going to be? This whole thing will be less than 0, right? And then we'll be done. So there's a question, why are the red terms less than 0 again? That's a good question, so let me take that. It's because of the fact that up here we proved this, right? We said that assume that f of u is less than 0, and we just kind of orchestrated some calculations to pull out the fact that this inner product will be less than 0, which is what motivated us to define the p. Okay, so we're reusing that fact, and so and so now we need this thing to be strictly less than 0, and so now what we have is that this quantity, if we can make it small enough, we're done. But we can make it small enough, right? Basically, we can choose t. T can be arbitrarily close to 0. And so in order to satisfy this, we can always choose a value of t such that this is true. And therefore, we can always find some p that is closer to c than d is. Okay? Does that make sense to everyone? I'm going to pause a little bit because this was like a little bit of a complex argument. Okay, so I'm looking through the questions. So it says, even if the other term is not in the gap, but more negative. So, okay, let's look at a couple of things, right? First, let me write some things down. Okay. First, recall that t belongs to 0, 1. Okay? So t can be arbitrarily close to 0. Okay? Now, if t is strictly less than, let's say, 2 times inner product of d minus c, u minus d, divided by norm squared u minus d. So now say, let's think about this another way. I want to show that this is true. I don't know that this is true. But I get to choose what t there is, right? So if I was to choose t such that this was true, right? T was smaller than this quantity. Then cross-multiplying and rearranging gives me this inequality. Does everyone see that? Okay, everyone focus here for a minute. Tell me if you're understanding this or not, because if you don't tell me, then I won't know. So good. So you choose a t such that this is true. Now remember that we know that this numerator term here is positive because this inner product is negative and we have a minus sign. The denominator is also positive. So this is a positive number. So this is some number that, as long as t is smaller than this, we're good. Now, if this number, and all we have, if this number is greater than 1, then any t between 0 and 1 will work. If this number is less than 1, then any number here works. Does everyone see that? Okay, good. So I see a question, why not just set t exactly equal to 0? So if you set t exactly equal to 0, then your u would be exactly the point D, right? And then P would also be exactly the point D. And therefore, you would not get a contradiction because you would get D, you wouldn't find a different point. But the point is here, by choosing a T that is strictly different from 0, we can find another point that contradicts the minimality of the distance between C and D. Okay? So if we choose this T, people wanted me to write this down, so then we can infer that T times U minus D squared plus 2D minus C, U minus D, is strictly less than 0, which implies that C minus P norm squared is strictly less than C minus D norm squared. And let me say why this is true. Let's label this equation as, label this whole equation as star. This is by star. Okay, so then this contradicts the minimality of the distance between C and D, which means we're done. Okay, therefore, we had a wrong assumption, which means that f of u must in fact be greater than or equal to 0, and f of x must be a separating hyperplane. Got it, everyone? Okay, questions. I'll pause for a minute, see if there are any questions in the chat. Okay, this is pretty obvious to me when looking at the picture in 2D. Is it just the mathematical proof for dimension greater than 2D? So yes, partly you have to prove it for things that are greater than 2 dimensions, but also pictures are deceptive just because pictures are great for building intuition, but you always have to take a geometric proof that you see by picture and make it rigorous. Okay, so that is something that is very important to do. Okay, so just a quick recap of what we did in the proof. So we assumed that there were 2 points C and D that were the closest to each other. We said, let's consider the hyperplane that bisects this line and is orthogonal to the line joining them. That's our separating hyperplane. And we said that, well, if possible, let's say that there is some u on that belongs to D that is on the wrong side of the hyperplane. So f of u is less than 0. And what we did was we showed that if that is true, then this vector u minus d gives us a direction. And if we travel in that direction, then we can get closer to C than D itself is. So we can move some small, tiny distance t along this direction that allows us to get closer to C. And we found such a P. We proved that this P must belong to D by the convexity of D. And then we said that, well, we proved that actually C minus P squared is less than C minus D squared. And this is under the assumption that this f of u is less than 0. But if that is the case, we're contradicting the minimality of the distance between C and D, and therefore this hyperplane that we considered must actually be a separating hyperplane. Okay, so hopefully that gives you a sense of the proof. I'm happy to answer more questions in office hours. This is a more involved proof than many things that you will see. But we will use some techniques along these lines again when we start getting to linear programs and LPs. Don't worry about memorizing this proof or something. No one will ever ask you to reproduce the entire proof of the separating hyperplane theorem on an exam or something like that. The point is to learn how to turn these geometric intuitions into algebraic proofs. Okay, so that concludes that section. And I will move on now to talking about convex functions. We talked about convex sets. We talked about the separating hyperplane theorem, which is going to get used in a couple of lectures from now, but we're proving it today. And now we're going to start considering the case of these functions. Let's say f is a function from Rn into R. And f is called convex if the domain of f is a convex set and you have this following property. The function evaluated at any convex combination of points is always upper bounded by the weighted sum of the points of the function values at the points themselves. Okay, so let me move this all onto one page actually. Okay, so what I'm saying is that if I have some x and some y belonging to my set, then I have not a vector theta. I have theta times x plus 1 minus theta times y should always be upper bounded by this quantity. I find it quite unintuitive to remember which way this inequality goes. And I always get confused. So I find it much easier to think about this in terms of a picture. So convex functions, I like to think of them as cups. And remember, if you have a convex function, it's going to be easy to minimize, so you can be happy. So it's a good way to remember which way is convex and which way is concave. Typically, we always develop theory for convex functions. I don't know why, but everything basically applies with the reverse inequality sign for concave functions. So we're going to be talking about convex functions, convex optimization, and we're going to be talking about minimization problems. And minimization problems are easy and nice in the context of convex optimization and convex functions. Maximization problems are easy when you have concave functions. But one easy way to remember is the following. Oops. Here, of course, this, I should write theta between 0 and 1. This inequality is called Jensen's inequality, which will be something that you should know the name of. But in general, what does this inequality mean? So the much nicer way to think about this is in the context of a picture. So let me draw a better convex function. So let's say I have some axes here, and I have some smiley face convex function like this. So it looks like a nice bowl. Let's say I have some x here, and I have some y here. And then I want to look at first, what is the function value at the weighted sum of these points. So this vector, theta times x plus 1 minus theta times y, that's going to be somewhere here. And so the function evaluated at that point is going to be somewhere here. Okay? On the other hand, the weighted sum of the points of the function values, so now this here is f of x, this point is f of x, this point is f of y, and the weighted sum of these points will be here, f theta times f of x plus 1 minus theta times f of y. And this is saying that a function is convex if this weighted sum is always above the function value. So a quick way of thinking about this is to say that the chord, right, the chord that joins f of x and f of y is always above the function. If I had a function that was looking like this, the chord is below the function always, and that's a concave function. Whereas here in a convex function, I have that the chord is always above the function. Does everyone see that? Yes, no? Questions? Okay, great. So this is the key property. Jensen's inequality is something that we will use over and over again. And kind of, maybe you can start to see intuitively, like if you have, a function such that it has this property, right? That the chord is always above the function. Like the chord is here, any chord you draw is always above the function. It's very hard to have multiple minima, right? Basically, if you're kind of imagine tracing this out, sweeping these chords out, what you're going to see is that intuitively, picture through the picture, that there is going to be one minimum, and that's what we are going to show for convex functions. And you'll show this one way on your homework, we'll show it a different way in class, but this is the fundamental property that makes convex functions useful and exciting. Okay? So there's a question, so can we think about a convex function as one where the local minimum is always the global minimum? I would not recommend it. You can say that if a function is convex, then the local minimum is always a global minimum. But there might be other non-convex functions that also have different properties. So I wouldn't necessarily just think of convex, think of it as Jensen inequality. Okay. So the one thing that is very useful to do is to have connections between convex functions and convex sets. And the way to do this is through the epigraph. And for those of you who did discussion yesterday, you've already seen the epigraph. Those of you who are going to do it Friday will see it tomorrow. But I'm going to define the epigraph of f as basically the set of all the points that are above the function. So for this particular function here, the epigraph is all of this. Okay, that's the epigraph of f. So the epigraph, to formally define it, the epigraph of f, let's say I think of it as all pairs x comma t, such that x belongs to the domain of f, and f of x is upper bounded by t. So basically, whatever the function value takes, it has to be lower than that t. If that's true, then therefore basically every line, every vertical line above this is in the set. Okay? That's the epigraph. And the nice property that you have is that f is a convex function if and only if the epigraph of f is a convex set. Okay? So we're not going to prove this property in class today. This will be on the homework, and you can prove it there. But basically, this is true. Okay? Good. So now I want to get to kind of one of the main other characterizations of convex functions, which is what we call the first order conditions. Okay, so here I want to consider an f that is a differentiable function. Okay, and again, let me just think of f as going from Rn to R. Remember, not all convex functions need to be differentiable. For example, what's an example of a convex function that is not differentiable? This function is a convex function that is not differentiable, right? There's no derivative here, it's undefined. The absolute value function is a great example. But here, we're considering those convex functions that are differentiable. Then f is convex if and only if domain of f is, not domain, sorry, what am I writing? Sorry about that. If and only if I can write that f of y greater than or equal to f of x plus gradient at x times y minus x for every x comma y belonging to the domain of f. So what is this saying? This is saying if you consider some point y as a perturbation from a point x, you can write Taylor's theorem, right? You can write Taylor's theorem to find f of y in terms of f of x, and this is the first order expansion of Taylor's theorem. Everyone remember that from the vector calculus lecture? Yes, no, maybe? Don't think of this is like, it's important that you see what this is, that this is the first order approximation using Taylor's theorem. Then what you see is that basically f of y is always above this quantity. And one way to think about this is that the tangent line is always below the function, right? So basically, if you have a convex function, and I take some x here, this is kind of always going to be below. And yes, this is f of y. Sorry if my handwriting is not clear. This is f, this is f. This is called the first order condition of this for a convex function that is also differentiable. Why is this a particularly powerful condition? What is the implication of this? What does this mean? What this means is that if now I have a point gradient such that the gradient of f of x at that point is 0. What if I find some x star such that f of x star is 0 and f is convex, of course? What can I say? Then I can say that f of y is always greater than or equal to f of x star plus 0 times y minus x, which means that f of y is always bigger than f of x star. This is true for every y in the domain. Therefore, x star is a global minimum. So, if you find a local minimum, as in you find any point where the gradient is 0, what that implies is that by the first order conditions, this must actually be a global minimum. Everyone see that? Yes, no, virtual nods? Yeah? Only one person sees it? Okay, no, multiple people see it. Good. Okay, thank you. Excellent. Of course, now we have to prove this, right? I just gave it to you, just fell out of something. But now we actually have to prove that this is true. But this is the important implication that makes the study of convex functions so attractive. This is only true, great question. This is only true for convex differentiable functions, correct. So yes, this proof that I have given you is only true for convex differentiable functions. In your homework, you will do another proof that shows that every local minimum must be a global minimum that relies only on Jensen's inequality. That's called a zeroth order proof as to a first order proof, basically, because like in Taylor's expansion, this is the zeroth order term. X to the 0 is what is being used here. Here is x to the 1 is the first order term, second order term, so on and so forth. So this uses this first order condition, but you can use this zeroth order condition to also show the same thing in a different way, and that's going to be on the homework. So proof of first order condition. So there's two directions that we want to prove. This is if and only if here, right? So if and only if means you have to prove both directions of the implication. So we'll do the first one, and if we have time, we'll do the second one. So first, if f is convex, then the first order condition holds. Okay? So how should we prove something like this, right? Well, clearly we have only one thing. We have Jensen's inequality if f is convex, so we have to use it. So let me just write it out. So I know that basically for, I have some f of, let me call it 1 minus t times x plus t times y. This is less than or equal to 1 minus t times f of x plus t times f of y, right? Everyone see this? This is just Jensen implies this. And let's just, here, I'll just write this out for scalars. The exact same thing will hold for vectors, but there's no particular need to add that complexity, so let's just assume scalars here. Okay? So I want to be able to use this to get something that looks like this, right? So this thing has some f of y on this side, f of x on this side, and what I know is something like this. So let me just rearrange the terms to kind of pull out the f of y on one side, right? So if I do that, I get t times f of y here is greater than or equal to minus 1 minus t f of x plus f of 1 minus tx plus t times y. Okay? And then again, doing just some rearranging. I feel like I did something wrong. No, okay. I think maybe hopefully it's right. So I get t times f of x minus f of x plus f of 1 minus t times x plus t times y. Okay, so I wanted to have f of y and f of x plus something, right? That's what I wanted. I'm kind of getting there. I have this and I have this. So what do you feel like doing here to make it look more like the first order conditions that we want to get to? What's an idea? Yeah, we want to take some kind of limit. What's an even more simple thing that we want to do first before taking a limit? We definitely want to take a limit. Divide by t, right? Exactly. So here I have this t times f of y greater than or equal to this. Let me copy what we want to get to here so that you all can see it. Maybe that will help. Copy, paste. So I'll put it down here. Like this is what we want to get to, okay? So if I now divide this through by t, I can say that this is f of y greater than or equal to f of x plus 1 over t times f of 1 minus t x plus t times y minus f of x. So I want to make this look kind of like a derivative on this right-hand side. So this, I'm just going to rewrite so I can rearrange this, right? To write this as can pull out the x plus a perturbation from x. This term is exactly equal to this term. Okay, so I'm just trying to kind of make this look like a derivative. And now I definitely want to take some kind of limit, right? So let's just remind ourselves, what is the definition of f prime of x? So recall, f prime of x is the limit, let's say as delta x tends to 0, of f of x plus delta x minus f of x divided by delta x, right? And if here I have a t in the denominator, so not quite a delta x, right? The units are off. So to make this match up, what do I want to do? I want to say, like, if I have delta x, let's say equal to t times y minus x. So if I take the limit, move this down. So if I take prime of x is equal to limit t going to 0 of f of x plus t times y minus x minus f of x divided by t times y minus x. So this is a scalar, and now it has the right dimensions of y times x. So it has the dimensions of the vector. So if this is f prime of x, what can I further say? That means that if I was to just take this and move it on the other side, this is not part of the limit, right? So I can pull it out. So I can say f prime of x times y minus x is equal to the limit as t tends to 0 of f of x, not a vector, plus t times y minus x minus f of x whole divided by t. Does everyone see what I've done here in terms of taking the definition of the derivative and manipulating a little? Any questions about this? Virtual nods, if people understand, say yes, something in the chat. We've lost everyone. Okay, I got one thumbs up. That's awesome. Thank you. Okay. If you have a question, ask a question. Okay, good. Now, with this, what if I take limits then on both sides of this inequality? Limit of t tends to infinity, t tends to 0. F of y remains f of y. Let me write that out, I guess. Take limit as t goes to 0, which gives me f of y is greater than or equal to f of x. And this is exactly the quantity that I computed the limit of here. So I can write this as plus f prime of x times y minus x, which gives me exactly what I wanted, the first order condition. First order condition. Okay, everyone see this? Great. No questions? Now we want to prove equivalence. Let's just prove the other direction. So to prove the other direction, which is that if the first order condition holds, then F is convex. Okay? Okay. So how would we prove this actually? We've done one direction. Just 1 second of how would ever think about how you would prove this. I'll take a sip of water. Okay, so obviously you'll start out by just considering some x comma y. Let's just consider scalars again. And we basically want to show now that Jensen's inequality is true, right? So if I now consider, let's say, some other point z, which is theta x plus 1 minus theta times y, I want to show that Jensen holds. So I want to show, what do I want to show? I want to show that f of z should be greater than or less than something. Is the chord above or below? The chord is above, so f of z must be below theta times f of x plus 1 minus theta times f of y. This is what I want to show, right? And what I know is that the first order condition holds, right? So I know that for every x comma y that belong to the domain, I have f of x, or rather, let's write it the way we've been writing it, f of y is greater than or equal to f of x plus gradient at f of x times y minus x, okay? So this here compares f of x and f of y. What do we want to have a connection between? We want to connect f of z to f of x and f of z to f of y, right? So what might be some points that you want to choose for applying this? Right, I'm just writing this in terms of x and y. X and y here are dummy variables, so don't get worried by the choice of x and y here. Maybe if it'll be easier for everyone, I can think of this as some other variables. Let me call these p, q, q, p minus q. That way you don't get confused. Okay. So since I want to connect z and x and y and x, and I want to have kind of f of x and f of y on the greater than or equal to side, I'm going to say, well, I can write that f of x is greater than or equal to the first order expansion of z, right? So f of z plus f prime of z times x minus z. And I can similarly write f of y is greater than or equal to f of z plus f prime of z times y minus z. Does everyone see this? I have no feedback from anyone. I have no idea if anyone's with me or all asleep or left the Zoom call. Virtual nod. Okay, thank you so much. Okay, good. Someone asked a question. Can you explain it again, please? I'm happy to explain it again. You just have to ask me. Okay, so we know the first order condition is true. We know that f of p for any point p is always greater than the first order expansion around any other point q. Since I want to connect f of x and f of y, I'm going to consider the connection between, I'm going to consider the first order connection, first order condition evaluated at, the point z, and I'm considering perturbations to x and y respectively, because I want to basically connect these things up. And I want to have f of x and f of y on the greater than side and f of z on the less than side, so I happen to choose it this way, right? I could also write something where the f of z is greater than f of x plus the derivative at x and z minus x. There's two ways of, connecting these things, but given what I'm trying to prove, this is the way that seems to make sense. And now I want to have basically, a theta on the f of x. So I'm going to try multiplying this by theta. And I want to have this 1 minus theta here. So I'm going to try 1 minus theta times this equation. And what that gives me is that theta times f of x, if I just add them together, plus 1 minus theta times f of y is greater than or equal to theta f of z plus 1 minus theta times f of z plus theta f prime of z times x minus z plus 1 minus theta f prime of z times y minus z. Which is equal to, very conveniently, I get here an f of z. And what do I get here? I get f prime of z times theta x minus theta z plus 1 minus theta y minus 1 minus theta z. Okay? Which is equal to f of z plus f prime of z times these two just add up to 1 theta x plus 1 minus theta times y minus z. But what is our definition of z? Z is exactly equal to theta x plus 1 minus theta y. So what is this entire term? This is just 0, right? This is equal to f of z, which is exactly what we wanted to prove, right? So now we have that Jensen's inequality holds for any point z, which is a convex combination of points x and y in the domain. Does everyone see that? Yes, no? Everyone? No, I think the expression in the second to last line is correct. Kai. I think this is correct. Okay, great. So that's it for today. Next class, we will pick up and start talking about gradient descent and then move into more general convex optimization problems in the following week. So hopefully I will be in person. Sorry for being on Zoom. And all of you take care, do your homework, don't get sick. Make sure you sleep at night, don't stay up all night and study. Take care. Thanks, everyone. Thanks for accommodating the Zoom lecture. I really appreciate it. I'll hang around on the link for a little bit longer in case people have questions. I'll do a little bit of office hours, but I will stop recording at this time. So thanks, everyone.